Hi class. So this section is 14.4, molecular definitions of acids and bases. We are going to look at two different types of definitions for acids and bases. The first one is the Arrhenius definition, and we're going to start with acids. So the Arrhenius acid definition is an acid produces an H plus ions in aqueous solution. So an H plus is a hydrogen ion, or also referred to as a proton. It's a proton because when we think back about atoms, atoms have equal number of protons and electrons, and that makes them neutral. But if you have an imbalance, meaning you have an electron taken away or an electron added, there is no longer a balance to that. And the charge that has more, meaning if you have more electrons, it's going to be negative anion, or you have taken away an electron, which means you have more protons, it is now a cation. And this is why we call it a proton, because this hydrogen ion does not have an electron, it only has a proton, so it's referred to as a proton. They mean the same thing. So HCl is a covalent compound. It's actually a gas, but when in presence of water, it becomes hydrochloric acid. And once in water, it separates into ions. And HCl is a strong acid, so this completely ionizes. So you only get the ions in solution. So what we see here is a forward reaction, one arrow, so it's only forward, and it completely ionizes. We're going to cover weak and strong acids later because not all of them do this. The hydrogen ion, or the proton, is very reactive. In aqueous solution, it bonds to water molecules, and this produces a hydronium ion, which is what you see here. It's an H3 plus ion. So we tend to use the hydronium ion and the H plus interchangeably. They mean the same thing. So let me show you an example of what I'm talking about here. Here is a reaction of HCl and water. This will ionize, and the hydrogen ion will go to and add itself to the water molecule. So now it produces a hydronium ion. If you look back here, this is the same reaction, but we're leaving it as a hydrogen ion and a chloride ion. We could actually add this into the same reaction like this and make it a hydronium ion. These reactions mean the same thing. One is expanded out, one is more of a shortcut, written in a short notation. Okay, so when we're talking about acids, the H is always in front when we're writing it in a formula, chemical formula. That's how if you look at a table, you will see all the H's in front. These are all acids. That's one of the identifying ways of knowing that it's an acid. You also I need to point out that there may be other hydrogens involved in the compound. Those are not part of the acid. They are part of the actual compound that was before it became an acid. So in this case, this is formic acid. So if we remove the hydrogen, then this is formate. So it was those H's, those hydrogens, are actually part of the compound that makes up the compound before it is an acid. To be an acid, we're adding a hydrogen to it, and this is making it the acid. And that hydrogen is also the one that's going to be ionized and come off. So if we write it in a structural formula, and you had to do electron dot structure and count everything out, what you would find out is that this hydrogen would not attach itself to the carbon because there's already filled with an octet. So it's got to fill itself, it's going to side with the oxygen, and this allows it to come off. And when it comes off, it will not take the electron with it, it will only keep the proton. So the oxygen here will have a negative charge, and this will come off with a positive charge. Okay, so the Arrhenius definition of bases. A base produces hydroxide ions in aqueous solution. So an example here is sodium hydroxide. It's Arrhenius base because it produces hydroxide ions in solution. It's also an ionic compound, and it contains sodium ions and, again, hydroxide ions. And when it's added to water, it's also a strong base, and it will completely ionize or dissociate, or it will only have ions in solution. Again, we'll cover weak acids and bases. Not all of them do this. Now, again, molecular compounds. You might see other compounds that have OH in them. This is not an acid or a base here. This is methanol. This is actually an alcohol. The OH here stands for alcohol. There's a list of acids and bases, and methanol is not one of them. So, strong bases are usually part of group 1 and group 2 metals. So there's calcium hydroxide, Actually, calcium hydroxide may not. Sorry, at the top of my head, I might be wrong about that being a strong base, but it is a base. Potassium hydroxide and so forth. But here, so don't always assume that when you see an OH compound that it's actually a base. In this case, this is methanol. It's an alcohol. If you go into organic, that will make more sense of what I'm talking about. Okay, so the Arrhenius definition was great when it was first proposed, and it worked for a while. It was the first definition that came up. Under the Arrhenius definition, acids and bases naturally combine to form water, and they neutralize each other out. That will come in another section when we start covering neutralization reactions, which I think is the next section. Now, the problem was it's very specific. The definitions are very, very specific, and they kind of cut out other compounds that have the same behavior as bases, but didn't necessarily contain the hydroxide ion in it. So the Arrhenius definition didn't always work. So it was expanded out, and now we go by the Bronsted-Lowry definition. The Bronsted-Lowry definition was two people, simultaneous but not working together in different countries, came up with this. So they both got the name of it, even though they did not work together on it. So the Bronsted-Lowry definition applies to a wider range of acid-base compounds. So this pretty much focuses strictly on the transfer of a proton. It follows the proton from where it left to where it goes and how it affects those compounds. So since a proton, since it's a hydrogen ion is a proton, the hydrogen ion is with the atom, excuse me, I'm getting tongue-tied. Remember, this proton does not have an electron with it, but the idea behind Bronsted-Lowry definitions is that we have a proton donor and a proton acceptor now, and that's how we look at it. We're not specifically looking at, for instance, a compound that only has a hydroxide ion, and that is what makes it a base. That's what Arrhenius definition for a base is. Now, it could be other compounds. That's a proton donor, proton acceptor. That makes an acid and a base. So a Bronsted-Lowry acid is an acid that is a proton donor. So it's giving its proton away. A Bronsted-Lowry base is a base that is a proton acceptor. It's going to accept that proton from that acid. And here, there's a little story about the two people working simultaneously. Here is the definitions for Arrhenius acid and base. An acid produces hydrogen ions in aqueous solution, and Arrhenius base is a base that produces hydroxide ions in aqueous solution. Here, we're specifically looking at an acid that donates its proton and a base that accepts the proton. So these are actually going from A to B. There's a definite start and a definite end. Where Arrhenius acid and Arrhenius base, one, the base had to have a hydroxide ion contained in the compound, and these really just say aqueous solution. There's really no what happened to them. So let's start looking at a Bronsted-Lowry acid. So according to this definition, if we're looking at this HCl and water, which we've already looked at before, that we need to figure out which is the acid and which is the base. And the best way to do that is to really understand what the definitions are to know how to look at this. So based on definition of a Bronsted acid, an acid is a proton donor. So we need to know which of these is going to donate a proton. And in this case, HCl is a strong acid. It's always going to ionize. So this one is an acid because it's going to lose the proton. And the water, based on what you can see here, if this is the acid, this has to be the base because the hydrogen ion has to go somewhere. So it's going to go to the water. So this is a Bronsted-Lowry acid, and this is a Bronsted-Lowry base. Why is the Bronsted-Lowry water a base? Because it's going to, and when the chemical reaction occurs, it's going to accept that proton. And you can see it does. So we end up with the ion of the acid with the hydrogen left. So we have a chloride ion and we have a hydronium ion. And the strength of an acid is determined by the concentration of hydronium ions. How many hydronium ions are produced? We'll cover that later. So this definition, clearly you can see where the H is going, and that's what we're interested in. We're going to follow where the hydrogen ion goes. Where did it, which one donated it and which one accepted it. So here you see there's acid is the proton donor and the water is the proton acceptor. And I just added this in so you can see a hydronium again. This is a shortcut, but when you're actually dealing with actual reactions, you'll see it like this. You won't see it like this. Okay, so the Bronsted-Lowry definition of bases. So remember, a Bronsted-Lowry base accepts a proton. So here we're dealing with water and ammonia. So now we need to figure out which one loses a hydrogen and which one gains the hydrogen. So if we look over here, we can see that we have an extra hydrogen that's now been added to what was ammonia, now is ammonium ion, and we have hydroxide ions. So this says that by this reaction, the water is the acid and ammonia is the base. So what we do is we can follow it over, and even though this is a base, this whole reaction still ended up producing hydroxide ions. So this is a very basic solution. So again, you can see down here, the ammonia is the base. It's going to accept the proton in the reaction, and we have our water, which is the acid, which is going to donate that proton. So when we're looking here, let's go back to HCl. HCl is a strong acid, which means that it is going to completely ionize in water. It will never come back together as HCl. There's not enough attraction. The water has a stronger attraction to the ions to keep them apart than there is for these ions of hydronium ion, the hydrogen ion or proton and the chloride ion to come back together. But that's not the case in the bottom one. We have where this one is only a forward reaction I'm getting tongue-tied here, by showing the arrow only in forward and there's no other arrow. So this is a complete forward reaction. But here we have two arrows. And that means that there's a forward reaction and there is a reverse reaction. And these are equilibrium arrows. So let's look at our forward reaction here. If we look at the forward reaction, what we have is we have an acid, because we determined that the water is going to lose a proton, and an ammonia is the base, and it's going to accept it. So in the forward reaction, we end up with products of ammonium ion and hydroxide ion. But there's also a reverse reaction happening here, and we have to look back at it. So an equilibrium means that, let's start here. There will be a reaction between these compounds, and then eventually enough products will start interacting with each other and push back into a reverse reaction of back into the products. And there will be an equal rate of this happening. So for instance, let's say that for every one of these that come together and react, there's also one of these that come together and react back. So that's what the equilibrium rate means. One's going this way, one's going back at the same time. And it will stay in equilibrium until a stress or something disrupts that equilibrium. So here, if we look at water, water loses that hydrogen, the proton, and it ends up as an ion of hydroxide. So if this is the acid, now we're going to give it this other part a fancy name of conjugate base. So if this is the acid, this would be the base. Here is a base, and it's going to gain the proton on the other side. So if this is the base, this is the conjugate acid. This is a conjugate acid, conjugate base. I'll explain what they are in a minute. Now, if we're looking only in the reverse direction, what we can see is that this is the acid and this is the base. That's where these terms come from. Why? Because the ammonium ion is going to lose the proton, and the hydroxide ion is going to gain it. So here we are again with an acid being donated based on Bronsted-Lowry definition, and a base accepting that proton. So this is where the words conjugate acid and conjugate base mean. So one here is an acid, so we need to locate the conjugate base that's attached to that water, and then ammonia also has a conjugate acid to it, which is ammonium ion. Now, what those words mean. A conjugate acid-base pair is a pair of substances that are related to each other by the loss or gain of a proton. So every reaction here, when we're dealing with an acid and base, has a conjugate pair. There's two of them going on here. I'm going to expand on that to give more examples, because it's sometimes very hard for students to understand what a conjugate acid-base pair is. But the first thing we need to talk about is amphoteric. Water. Water is one of a few substances that can either act as an acid or a base. So it can either accept or donate a proton. And it basically is determined by whatever it's reacting with. So in this case, ammonia had a stronger attraction to that proton than water did. So water could easily give it up. So that's why ammonia ended up being the base and water was the acid. Ammonia had a stronger attraction to it. But if water has a stronger attraction to a proton from another compound, then it will be the base. So it's basically what it's reacting with determines if it's an acid or a base in those reactions. So now let's go back to here. So this is asking, so now we have ammonium ion that's been produced and hydroxide ion. I don't know why I can't speak today. I apologize. So what was the base has now become the acid, and what was the acid has now become the base. So that's where we refer to them as a conjugate acid-base pair. We pair these up. So in this case, ammonia and ammonium ion are as conjugate acid-base pairs because they were related to each other by the transfer of a proton. So this received a proton, this base and conjugate acid-base pair. So these two are linked up because they're related by the transfer of a proton. And the same thing for the water and the hydroxide. They are linked up. They are a conjugate acid-base pair because, again, of the transfer of a proton. So here is, these are linked up. So this is a base with its conjugate acid, and this is an acid with its conjugate base. So in any acid-base reaction, there are two conjugate acid-base pairs going on. Each pair is related by the loss or gain of a proton. One pair occurs in the forward direction, and one pair occurs in the reverse direction. I have examples, so I will give some more to help explain this. So the first thing you want to do, this is hydrofluoric acid, and this is water. Out of the halogens, when they become acids, hydrofluoric acid, fluoride is the only halogen that is actually a weak acid. So it has equilibrium arrows in its reaction. The rest are all strong, like hydrochloric acid, hydrobromic acid, hydroiodic acid are strong. Okay, the first thing you need to do, figure out which is the acid and which is the base in the reactants. So in this case, it's already been labeled, but we should be able to confirm that. These both have hydrogens in them, so we don't know which one is. And remember I told you water can be either one, but it's based on whatever it's reacting with. So in this case, excuse me again, water is going to be the base. Why is it going to be base? Because it has a stronger attraction to that proton. So it'll take it away from hydrofluoric acid. So in this case, this is the acid, hydrofluoric acid. If we follow the forward direction arrow, we can see that the hydrofluoric acid loses the proton. And then if we follow here, so if this is the acid, this is the conjugate base. Now let's take a look at water. Water is a base, which means it's got to accept that proton. So if we look at just the forward reaction, it's going to gain that proton, and now we have hydronium ions that are produced. So now we have a conjugate acid to this base. Now let's take a look at the reverse reaction, because we have reverse arrows here. If we look at the fluoride ion and we follow it, we can see that the fluoride ion gains a hydrogen, and that produces the acid. So again, acid and conjugate base. And then here, if we go backwards, we have hydronium ions, and as we follow this arrow, it's going to lose one and produce the water. So then again, this is base and a conjugate acid. So we have a reverse reaction, we have a reverse reaction, and we have a forward reaction. So once you can determine what the acid is, you can determine what the conjugate base is to that acid, and once you determine the base, you can determine what the conjugate acid is to that. So if you have problems trying to see it, you can also write it out so you can see what's exactly happening. So again, this is just covering exactly what I've stated. Figure out which is the acid, which is the base. We've already covered this one. So water is the acid. It's going to produce hydroxide ions. So that this is the acid, this is the conjugate base. We have the base, this is the conjugate acid, and you can see. So an acid has to lose the hydrogen, proton, and so it's going to lose it. So here's the acid. It loses that proton and it's in its conjugate base, which is the hydroxide. And now, so that makes these two a conjugate pair, the water and the hydroxide ion. Now that proton had to go somewhere. So here is the proton. We have a base, and it adds a proton, which ends up producing a ammonium ion. So now we have another conjugate acid-base pair. We have ammonium and ammonia, and we have an ammonium ion, another conjugate acid-base pair. And I added the definitions so that you can keep it straight what exactly I'm talking about. So again, same thing. Here we have sulfuric acid and water, and then we have what you could call, there's two different ways you can call this. This is bisulfate, which is a weak acid, or you can call it hydrogen sulfate. Two names, they mean the same thing. So in this case, this has two hydrogens though. So when it's going to do this, so sulfuric acid is a strong acid. However, bisulfate is not. So let's just look at the first one, and then I'll tell you why I'm bringing that up. So in this case, which is the water, which is the acid? This is a strong acid, so this is going to be stronger than water. So it's going to lose one proton. When we're discussing acids and bases in Bronsted-Lowry and their conjugates, if it has two hydrogens, and we call this a diprotic compound or diprotic acid, it loses those hydrogens one at a time. And so in this case, one proton comes off very easily. And so it's going to react with the water. So we figured out which is the acid, so we have to find the conjugate base, and that is bisulfate. Now, over here, let's find the base. So we have the base, so if it's the base, it has to accept that proton. If we follow it, we have the conjugate acid in this case. And then if we were to complete this again, we would have to determine between sulfate and water, which one is going to, because you're going to add water to have this happen again, to remove it, and it would go on, but I'm not going to go there. Probably shouldn't have brought it up. So in this case, a base accepts a proton and becomes a conjugate acid, and an acid donates a proton and becomes a conjugate base. So the simple thing, the easiest way to do this, determine which one is the acid, which one's the base. If you know which one the acid, you can determine which is the conjugate base. And if you know the base, then you can determine the conjugate acid. Why do you need to learn this stuff? Because this is where we're going to start going into equilibriums. Chapter 15 would have covered equilibriums and buffers. Buffers also play a part into this, which is one of the last chapters in this, one of the last sections in this chapter. Okay, so let's do some testing of how you understand this. In each of the following equations, identify the Bronsted-Lowry acid and base. So this is in the reactants. We're not looking for conjugates yet, just the reactants. So in this case, let's look at A. We can follow it, and we can see that we are produced hydronium ions. That's only got to come from water. So that means this is the base, and this is the acid, because there's nitrate. So this is nitric acid and nitrate ion. So here is the acid, and here is the water. So now if we look at the bottom one, we have hydrofluoric acid, and we have water. So again, let's look on this side. This is a strong acid, so it completely also ionizes. Here we have equilibrium, so this is a weak acid. It doesn't completely ionize in water. So here we have hydrofluoric acid and water, and we can see again we have hydronium ions. So this has to be the acid, and this has to be the base. And that's true. So once you can figure those, then you can figure out what the conjugate acid and base are. But I've got more examples. So write the conjugate base for each of the following acids. So what that means is break these apart. Break these apart so that you can show what these are going to be separated out away from the proton. And write the conjugate acid of each of the following bases. So it's just easy for me to show you, and then we can go step by step on these. So we have hydrobromic acid, and it's not asking whether it's a weak or acid or strong. Don't worry about that. It's just asking to find the conjugate base. So we're going to disassociate this. So it's going to be always, if you notice there's a trend here, there's a proton. So we take the proton away, and here's going to be a bromide ion. Here is hydrosulfuric acid, and this one's going to have one hydrogen removed. So if you remove one hydrogen, you've got to show a charge because it's no longer balanced out completely. And then here we have carbonic acid. And again, we're going to remove one hydrogen. So you've got to show a charge because it's no longer neutral. It's not balancing out. But these will lose a hydrogen proton one at a time. Now, write the conjugate acid of the following bases. So now we're going to do reverse. We're just reversing those arrows. And if you notice, these two have charges and this one doesn't. So in this case, these had no charges, but when you disassociated them, you needed to have charges. Now, if we're adding hydrogens back, these should have no charge. But this one's going to have a charge because it's not balanced. You have to show that there's an extra proton. So in this case, we have nitrites, even I forget at times. We're going to have nitrite. We add a proton to it. That makes this nitrous acid. And then here we have ammonia. We add a proton to it. It is ammonium, and because you're adding an extra proton and it's not balanced, you have to show that there's an extra proton there, which is why there's a plus charge. And we have hydroxide. We're going to add a proton because remember the minus means an extra electron, so this will balance it out, and we have water. And here's just a definition to explain why this has an extra charge to it when the other ones didn't. Identify the sets that contain acid-base conjugate pairs. So we're just looking at these and determining which ones. So I'm going to show the answers and then let's break down why. So we have nitrous acid and nitrite. And these are an acid and conjugate pair because you can see if you remove the proton, you'll end up with nitrite. And then here we have carbonic acid and we have carbonate. This is not an acid-base pair because of the fact that it's jumped from, this one doesn't have a comma in it, it should have a comma, but this one it's lost both hydrogens, both protons, and we do not do that. We lose them one at a time. So this could not be an acid-base conjugate pair. And then we have two different entirely compounds here. So that's not even going to work at all. And here we do have a base and a conjugate acid because we have, you can see, once we add another hydrogen to this, that makes it hydrosulfuric acid. So this is a base and a conjugate acid. And then here we have a base and a conjugate acid because we've been covering this one.